How do you fly an aircraft when the flight controls no longer respond? United Airlines Flight 232, a McDonnell Douglas DC-10 registration N1819U, departed Denver Stapleton International Airport on 19 July 1989 at 14:09 local time. It was bound for Chicago and then Philadelphia, with 296 people on board. 67 minutes into the flight at 15:16:10, there was a large bang, followed by vibration and shuddering of the airframe. The NTSB describes the event as a catastrophic failure of the number 2 tail-mounted engine, with separation and fragmentation of the stage 1 fan rotor assembly, leading to the loss of all 3 hydraulic systems. The captain called for the shutdown procedure for the failed engine, while the second officer, serving as flight engineer, was shutting down the second engine. He noticed that all 3 hydraulic systems were showing 0 pressure and 0 quantity, resulting in the loss of all conventional flight controls. Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. This episode is titled No Flight Controls. The first officer stated that he could not control the aircraft, which entered a right descending turn. The captain took control and confirmed that the aircraft did not respond to the flight controls. The captain reduced thrust on the left engine, number 1, and the wings began to roll to a wings level attitude. The crew deployed the air-driven generator, which powered the number 1 auxiliary hydraulic pump, but this did not restore hydraulic power. At 15:20, the flight crew radioed the Minneapolis Air Route Traffic Control Center and requested emergency assistance and vectors to the nearest airport. Initially, Des Moines International Airport was suggested, but at 15:22, the controller said they were headed towards Sioux City, and if they would prefer to go there. The flight crew responded affirmative. The flight crew told the senior flight attendant to prepare for an emergency landing. The flight attendant informed the captain that an off-duty United Airlines DC-10 training check airman in the passenger cabin had offered his help, which the captain immediately accepted. He entered the cockpit at 15:29. The captain asked the check airman to go to the cabin and check the wings of the aircraft. Upon his return, he reported that the inboard ailerons were slightly up but not damaged, and the spoilers were locked down. There was no movement of the flight controls. The captain then directed the check airman to take control of the throttles to free the captain and first officer to manipulate the other flight controls. The check airman attempted to use engine power to control the pitch and the roll of the aircraft, which had a continuous tendency to turn right, making it difficult to maintain a stable pitch attitude. He also advised that the left engine number 1 and the right engine number 3 thrust levers could not be used symmetrically, so he used 2 hands to manipulate the 2 throttles independently. About 1542, the flight engineer was sent to the cabin to inspect the tail visually. Upon his return, he reported that he observed damage to both the right and left horizontal stabilizers. The aircraft circled 4 times before landing, mostly turning right, but also managing to make a left turn to approach Sioux Gateway Airport away from the city center. The captain specifically asked ATC for a routing that avoided areas of dense population. Fuel was jettisoned to the level of the automatic system cutoff, leaving 33,500 pounds. About 11 minutes before landing, the landing gear was extended by using the alternate gear extension procedure. The flight crew said they made visual contact with the airport about 9 miles out. ATC had intended for Flight 232 to attempt to land on runway 31, which was 9,000 feet long. However, ATC advised that the aircraft was on approach to runway 22, which was 6,888 feet long. The captain decided to maintain the approach to runway 22 rather than to try and turn left for an approach to runway 31. The Czech airman said that the aircraft was lined up and on a normal glide path to the airport. The flaps and slats remained retracted. In the last 20 seconds before touchdown, the aircraft speed averaged 215 knots indicated airspeed, and the descent rate was 1,620 feet per minute. The captain recalled that there was a high sink rate alarm. Smooth oscillations in pitch and roll continued until just before touchdown. The captain stated that about 100 feet above the ground, the nose of the aircraft began to pitch down, and he felt the right wing drop at the same time. Both the captain and the first officer called for reduced power on short final approach. The Czech airman said that based on his experience with no flap and no slat approaches, he knew that power would have to be used to control the aircraft's descent. He used the first officer's airspeed indicator and visual cues to determine the flight path and need for power changes. He thought the aircraft was fairly well aligned with the runway during the latter stages of the approach and that they would reach the runway. However, soon thereafter, he observed that the aircraft was positioned to the left of the desired landing area and descending at a high rate. He also observed the right wing began to drop. He continued to manipulate the thrust levers until the aircraft contacted the ground. The power was constantly changing during the approach. He added some power just before contacting the ground. The aircraft touched down on the threshold slightly to the left of the center line of runway 22 at 1600. The first contact with the ground was made by the right wingtip, followed by the right main landing gear. The aircraft skidded to the right and rolled to an inverted position. Witnesses observed the aircraft ignite and cartwheel. Firefighting and rescue operations began immediately, but the aircraft was destroyed by impact and fire. There were 111 fatalities, 47 serious injuries, 125 minor injuries, and 13 without injury out of the 296 people on board. Although 111 people died, 185 survived, which makes the accident both tragic and remarkable in terms of survivability. 78 of the fatalities resulted from impact injuries, while 33 of the fatalities resulted from post-crash fire and smoke inhalation, particularly in the collapsed section near the left wing box, rather than from the impact forces alone. Tragically, 10 of the fatalities were infants, and NTSB issued safety recommendations calling for the tighter regulations on infant restraints. That combination of total hydraulic failure, remarkable crew resource management, and major survivability lessons is why UA 232 remains so prominent even decades later. The Safety Board believes that under the circumstances, the United Airlines flight crew performance was highly commendable and greatly exceeded reasonable expectations. After carefully observing the performance of a control group of DC-10 qualified pilots in the simulator programmed to simulate the accident aircraft, it became apparent that training a comparable attempted landing would not help the crew in successfully handling the problem of the loss of all three hydraulic systems. Therefore, the NTSB concluded that the damaged DC-10, although flyable, could not be successfully landed with the loss of all hydraulic flight controls. Each individual landing parameter, speed, touchdown point, direction, attitude, and descent rate, could be controlled separately, but it was virtually impossible to control all parameters simultaneously. The National Transportation Safety Board determined that the probable cause of this accident was the inadequate consideration given to human factor limitations in the inspection and quality control procedures used by United Airlines engine overhaul facility, which resulted in the failure to detect a fatigue crack originating from a previously undetected metallurgical defect located in a critical area of the Stage 1 fan disc that was manufactured by General Electric aircraft engines. The subsequent catastrophic disintegration of the disc severed all hydraulic lines to the flight controls. UA 232 remains one of the very few major transport aircraft accidents in which an internal aircraft failure led to the loss of all hydraulic flight control systems. UA 232 did not by itself end the tail-mounted engines or trijets. It exposed a catastrophic common cause failure mode in the DC-10 installation, an uncontained tail engine failure damaging co-located hydraulic systems, and it strengthened the case for better physical separation and protection of critical systems. The commercial decline of the tail-mounted engine wide-body trijet was driven mainly by ETOPS, high bypass engine reliability, fuel efficiency, maintenance cost, and the rise of large underwing twin jets. One of the NTS board members dissented from the official findings, saying that the accident event was foreseeable, even though remote. Jim Burnett's dissent opinion was that General Electric aircraft engines, United Airlines, the Douglas Aircraft Company, and the FAA failed to detect, correct, contain, and certify the engine failure mode properly. Burnett's point was that remote should not have meant dismissible, especially where feasible design measures could have reduced the hazard. He noted that the existence of post-accident retrofits showed that additional protective steps were technically possible. So what is our conclusion? UA232 did not end tail-mounted engines as a configuration, nor did it single-handedly end the wide-body trijet, but it exposed a deeper certification lesson. Redundancy is not enough if redundant systems remain vulnerable to the same debris field, the same structural zone, or the same uncontained failure mode. Jim Burnett's dissent captured that broader lesson. A remote event is not dismissible when its consequences are catastrophic and when feasible design measures can reduce the common cause risks. The legacy of UA232 is therefore not simply that an exceptional crew achieved the nearly impossible. It is that aircraft design and certification must consider not only the probability of a failure, but also the physical consequences when that failure defeats supposedly independent systems. Many thanks for watching. If you like this analysis, then please subscribe to ensure independent aircraft investigations continues.